Hello everyone. In our lecture series based on vector analysis, today we are going to discuss one of the most important theorems in vector analysis, which is Stokes' theorem. Well, this Stokes' theorem uses curl of a vector function. And as we have studied this and discussed this in the previous video, that curl is associated with line integral and surface integral, because usually we have a boundary which encloses some surface. As you can see here, this blue colored region, the boundary C shown with the arrows, the girl is running round the track, round the boundary, it is enclosing some surface, and that surface is denoted by S. And you also know, whenever we have surface only, we always represent unit vector, which is perpendicular to the surface and which actually denotes the third direction, because surface captures two dimensions only, because it is an area basically. And then we always show a unit vector, which is our n cap, which is always perpendicular to the surface, and it points in the direction of the third direction, the third perpendicular axis. So let's get started. Let's have a look at this statement. It states that the line integral, because we know that this Stokes theorem involves curl, and curl involves line integral and surface integral. So the line integral of the vector function A, because we know that vector function A is spread over this entire region. Okay, this entire region, vector function A is spread over this entire region that I'm showing with this yellow color. And then we have just considered a particular boundary in this region, and that boundary is a closed boundary, and being a closed boundary, it is actually enclosing some surface. So the statement says that the line integral of the vector function A round any closed curve C is equal to the surface integral of the normal component. So normal means n cap has to be there. Normal component of the curl of that vector function over the surface S, of which the curve is a bounding H. So we have to relate the line integral over the boundary with the surface integral of the surface. You must have observed in Gauss divergence theorem that there we considered a closed surface S. We considered closed surface S, which was enclosing a volume. You can see these are the 2 points of distinction between Gauss divergence theorem and Stokes theorem. Gauss divergence theorem, we have closed surface S, because again we consider some region in which vector field is there, and then we consider some closed surface S which encloses volume V, and then we divide that complete volume V into large number of small volumes, and then we pick a particular volume and solve it. Whereas in Stokes theorem, we consider a closed curve C. See, it's just a line. You can see the arrows that have been drawn, the boundary, it's simply a track. So we consider closed curve C, and being a closed curve, it encloses surface S. So you can clearly see the difference. So Gauss divergence theorem deals with surface and volume, whereas Stokes theorem deals with the line integral, line or curve and the surface. And if you go through both the derivations, in each and every step you would find some point of distinction between the two. You can actually differentiate between the two if someone asks. Alright, so now we have the statement. We have to relate the line integral of the vector function, and line integral would be along closed curve C, because it only involves one dimension, and that has to be equal to the surface integral, because the closed curve is actually enclosing some surface integral of the normal component. You know, whenever there is surface, we have to use the normal component, which is unit vector n cap, and then that has to be of curl of the vector function over the surface, because ultimately surface integral, if we are using it, then it has to be over the surface. So how would we write it down mathematically? So let's write it down mathematically. Mathematically, it means line integral of the vector function A. So line integral of the vector function A, and now we know how to represent it, because obviously we need the variable along which, or with respect to which, that function is changing. So we have to specify that integration is with respect to which variable. So A dot dr. Round any closed curve C. It's written round any closed curve C. So it's a closed curve. You know how do we represent a closed? Anything which is closed, we represent it with a circle. And to actually denote that which curve or which surface are we talking of, we always mention the name. So here the curve considered is C, so we have written C here. So now that is equal to the surface integral. So first put the equal sign, and then that is equal to surface integral, so double integrals of the normal component of the curl of the vector function. So normal component of the curl. So how do we write curl? That is del cross A, and then it's saying normal component of the curl. So that means we have to take the dot product with respect to the normal component. This is how we always do. Whenever we have a surface, this is the thing that we always do. When we were understanding surface integrals, you must have noticed that there we used to write A dot ds. And then this was basically A dot n cap ds, because ds was simply the small change in surface, but the real dot product that we often take, that is with respect to the n cap, the unit vector which is perpendicular to the surface, right? So whenever there is surface, we have to make use of n cap. Just keep this in mind. And now you see that some things are fixed. We are always using, since you must have seen in all the derivation, whenever there was surface integral, we have used n cap along with it. For surface integral, double integrals, whenever there is something which is closed, we always represent it with a circle. For line integral, it's always the dot product with respect to dr. So these are the fixed things, and you also know the meaning why we are doing so. So there is nothing that much complicated about physics and the derivations. Often students find these two derivations, Gauss divergence and Stokes theorem, really difficult. But I really don't see what's the reason of finding it that difficult. If you know the vocabulary, see all these, the mathematical formulae that we are writing, the expression that we are writing, these are the vocabulary of physics, vocabulary of vector analysis. If you know the meaning, you're good to go. Okay, so let's continue. So this line integral we have taken, and then the surface integral involves the integral over normal component of curl of the vector function. So we have written, and this is not done yet, we have to mention ds, because ultimately surface integral means the integration is over the surface, so you have to represent that surface element, right? Okay, anything left? Now let's see what's left in the statement. So we have done till here of the curl of the vector function over the surface S, of which the curve is a bounding edge. Okay, so this curve C is actually, it's bounding the surface S. So we would represent here that which surface are we talking of? We are talking of the surface S. So now that's the complete mathematical definition or mathematical statement of Stokes theorem. Either you write the statement or you write it mathematically. But in general, in exams, you have to write both. That will, this particular statement has 1 mark and this mathematical expression has 1 mark. So you have to mention both. Now let's start with the proof. Let's consider a surface S with C as its boundary. So you can see the figure A, which represents that we have a boundary, a curve C, which is a closed one, and it is enclosing some surface S. And being a curve, C would be having the vector dr associated with it, because we have to take the line integral if we are talking of that curve. To find the value of vector function A over the curve, we have to find the line integral. So you can see the vector dr and the vector A as well. So basically, in case of line integral, the direction of the position vector dr is almost same. You can see that. And the unit vector is also in the same direction as that of the vector function A, whatever vector we are considering. In case of line integral, unit vector also lies along the same direction, and that's why we don't represent it, because ultimately we have to take dot product, and we know that dot product is what? If we have to consider A dot dr, it would be A dr cos theta, and theta would be 0 and cos 0 degrees 1. So ultimately we would be having ADR. So there is no use of showing n cap, because after all it would be removed. Even if we have this closed curve C, which is enclosing surface S, but to find the value of vector function, it's not easy to just get the value over the entire surface or over the entire curve. Now you know that it's not possible for us to get the value over the entire region or entire surface in just one step. We have to break it down into smaller segments. So first step is that we are drawing a line AB. So we have drawn a line AB, and which has divided this entire surface or area into two parts. Basically, you can see there are two equal parts, but now we can differentiate these two parts, and we have shown that instead of the figure A, in which there was just one boundary C and there was just one surface S, since we have divided that into two parts, now we have two boundaries C1 which encloses surface S1. So the surface enclosed between AB and C1 is S1, and then we have this curve C2 which encloses surface S2. So the surface enclosed between AB and C2 is S2. Alright, now we can find the line integral of A around the boundary first. That is easier for us to do, so let's do that. Line integral around the boundary of delta S1. So delta S1, because of course this surface area is, the surface is really small, so delta represents the small change or that particular small region of area that we are considering. So the boundary of surface S1 is C1. So let's find the line integral. That would be A dot dr1. So here I just say that we have the vector function, but now here this line vector, this is dr1, and here this is dr2. So A dot dr1 over the curve C1, which is a closed one. So this is the line integral around C1, and then line integral around C2 would be, since that again is a closed one. See, you can see that that would be A dot dr2 over this closed curve C2. So this is our equation 2. You can see that this is a closed curve. Now the closed curve for surface S1 is C1 and then ABA. So it goes around this C1 and then this BA. Alright, you can see the arrows that the curve is going along C1, it is going anti-clockwise, and then it moves along B to A, and in this way it is a closed one. And for S2 it is that you can see it's again going anti-clockwise, it's going from C2 and then it enters A and then it goes along AB and then again. So both are closed curves and we have represented the line integral. But these two equations 1 and 2 that we have written, that is only for the curve C1 and curve C2. That's not for the entire. Or let me just do one thing, that since here I'm just representing the C1, but that C1 actually includes that BA track as well. So I have not mentioned it. Why? Because here I have written that line integral around the boundary of surface S1, which includes C1 and BA. And for S2 it is C2 and AB. Now can you see that for BA, for the surface S1, the curve is going from B to A. Here you can see that for surface S1 it goes like this, see, and it comes and it moves like this. It goes from B to A, alright. And for surface S2, it goes from curve C2 and then it enters AB and it moves from A to B. This is how it is moving. So when I'm saying that line integral around the boundary of S1, so I'm considering both. I'm considering the entire integral around the closed curve, which includes C1 and BA. And for S2, it includes C2 and AB. But can you see that in case of S1, the direction of integral is opposite for this center, for this middle track. The line AB that we have drawn, for surface S1, we are going from B to A, and for surface S2, we are going from A to B. We are going from A to B. These are opposite. Line is same, so the track is same, magnitude will be same, but it's being traversed in opposite direction. For S1, we are going from B to A along the same line, along the same track. For surface S2, we are going from A to B along the same track, but in opposite direction. So these two directions, the line integral along this AB track for the both surfaces would cancel out. Here, as line AB is common to both the surfaces and is traversed in opposite direction in the two integrals, it's easy to see that for surface S1, it's been traversed from B to A, and in case of S2, it's been traversed from A to B. So the line integral of A along this common boundary being equal and opposite, because the boundary is same, you can see it's AB, so magnitude is same distance, but direction is different. So being equal and opposite, they cancel each other when considered together. So the rest of the boundary C1 and C2, they are identical to the original one C. You can see that in figure A, this curve, the original boundary C was going in anti-clockwise direction, and here, even if we have divided this picture into two halves and we have obtained two boundaries now, C1 and C2, but still they are just exactly identical to the original boundary C. C1 is moving along the anti-clockwise direction. You can see the arrow matches with that in figure A, and C2 is also moving in anti-clockwise direction, and you can see the arrow which matches with the arrow which is in figure A. Okay, so ultimately they are same, and we have found it's the only thing that the AB is common, the side AB is common to both the surfaces, and it's been traversed in opposite direction in both the surface. So the line integral along it would be equal but opposite. So they have to be cancelled out. So that's why they cancel each other, and we have removed it from the picture. All we are left with are these two curves only, the two boundaries. Hence the common, we can say, the line integral around the closed curve C, that is equal to the line integral along the closed curve C1 of vector function A plus line integral of vector function A along C2. And this position vector is also the same, so we can just simply mention A dot dr in both the cases. Because these two curves are almost similar to the curve C. There is no difference. So in curve C, as you can see in figure A, we had the common line or position vector dr. If we are saying that this C1 actually resembles the original C, and even C2 also resembles the original C, so the dr1 and dr2 are also identical to the original dr vector. That's why we can simply replace them with dr. In reality, we can draw as many boundaries or as many tracks the way we made just AB. So we can draw as many lines within that particular surface as we have drawn in figure C. You can see that. And we would get a lot of curves. Now, since it's been divided into large number of small surfaces, all the boundaries you can see, we are getting different curves. This is one curve, then two curve, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so in this way we would get a number of curves, and it all depends on how many surfaces we have divided this complete surface into. More the number of surfaces, more the number of curves, more the number of boundaries that we will obtain. So generally we can mention that A dot dr along the closed curve C, that would be equal to A dot dr along n number of closed curves. So we are talking only of the boundary right now. Here in figure B, we only divided it into two halves, two equal halves, just by single line, just for ease to understand the concept, just to understand that no matter how many lines you draw, ultimately what would be of concern or what would be left for calculation are just the boundaries. Okay, only the curves, our outer boundaries will be available for us for calculation, and that we have seen here very clearly. That even if we had AB line with us, but ultimately since it is traversed in opposite direction in both the curves, so it just cancelled out, so it's meaningless. It's the line integral along AB is meaningless for us. All we are concerned with are the curves, the two curves. So, but in actual what we do is we divide the surface into large number of infinitesimal surfaces, very small surfaces. So there would be large number of surfaces, and then obviously we would obtain large number of curves. You can see here that the number of boxes that we have drawn, we have obtained around 18 curves. So, but in reality we draw even more surfaces, even more lines, so we would be having even more curves with us. So this is the general representation. If the area is divided into large number of small areas, and definitely they would be having different boundaries. In that case, if we write down the line integral of vector function A only along one curve, let's say C1, then that would be equal to this curl of vector function A dot delta S1. And now just see that this delta S1 is basically a vector. We have drawn a vector. Why? You know it includes the surface only, the magnitude, plus the unit vector. So always remember that this is n cap delta S1. Ultimately, the dot product would be with respect to n cap because it's the surface. When we did the curl of a vector function and we understood its physical significance, then we studied that mathematically curl of vector function is equal to this line integral over the closed curve which encloses a particular surface S per unit area. And the area that we are considering, that's really very small. That's the reason now that here this is A dot dr portion and this has been multiplied. Okay, so it's curl of A, which is represented by del cross A dot delta S1. Here this is simply a magnitude per unit area, but see this n cap is also there, so that's why it's dot delta S1, because this delta S1 vector includes both n cap and delta S. Thus we can write down that for C2, the line integral of A along curve C2, that would be equal to the curl of vector function A dot product with the surface S2 whose boundary is C2. And similarly, for the vector function A and its line integral along the curve Cn, that would be equal to the curl of vector function A dot delta Sn. So we can write this for number of surfaces having number of curves, right? So this is the line integral for individual surfaces. But what if the entire? Because ultimately we want to know the answer for the entire region. You can see here we are concerned with this entire surface S and we want to know the value. Or we want to know the value around this entire curve. Even if we have divided it into many number of surfaces and thus we have obtained a number of boundaries, but ultimately we are concerned with the entire region because that is the chosen region. That is the chosen region where we want to find the value of vector function A. So in that case, we have to simply add them up. So we have this A dot dr and we have the closed curve C, and that would be equal to the summation. We have to sum up all these quantities. So this plus we have the curl multiplied with the surfaces, and then this would go on till the surface Sn. In just one step, we can denote them by summation, right? Whenever we have large number of quantities, we denote them by summation. So in simple sense, that would be del cross A dot, let's say delta Sn. We'll keep the n as our variable, and this n would be a large number, let's say infinity, and this S, here we have this thing. Let's represent not by n, by I, because I will vary from 1 to n as we have written. We have written that in this step del cross A dot S1, then dot S2 and so on up to Sn. In common sense, we would represent that all these surfaces, the subscripts 1, 2, 3, 4, so on up to n by I, and this I is varied from 1 to n. And now the limit is that this n is going to be really large number. Right now the summation means that it's a countable one, but we know that no, whenever we make the divisions, when we subtract a region or when we divide a region into large number of sections, the number of section is really large. So this n would tend to infinity, and this delta Si, the surfaces that we are considering, they are going to be really, really small. That's why delta Si tends to 0, which shows that the area is going to be very small. This is how it is. Again, I'm explaining that we have n number of surfaces and we are adding them up. So del cross A dot delta Si, I represents the common, it's the common sign or symbol for all those surfaces, and it is varying from 1 to n. So that's why we have written I equals to 1 to n. But now what we know about n is that these number of surfaces, they are going to be really large. They are going to be infinite. So n is tending to infinity. And what about the surfaces? Because if we are going to make really small surfaces, only then it's the possibility that whatever region we have considered, the number of surfaces would approach infinity, and that is only possible if the surfaces that we are considering, they are really, really small. So that's the reason that delta Si is tending to 0. It has to be really small. Now comes the question that if we know that the number of surfaces are going to be infinity, then is it possible for us to count them? To count the infinite number of surfaces? No, it's not possible. Whenever infinity comes in, then it's really difficult for us to do the counting. So summing up, summation represents, this summation is for discrete items, for the items which are countable. But if we are not able to count those things, then we have to jump to integration instead of this summation. So that's the reason that when, and you can also see that the surfaces are really small. So the whole region would look almost continuous even if it's not. Even if we have divided it into large number of surfaces, it will not be able for us to count them and actually differentiate between one surface and the other since it's really small. So when this kind of difficulty is there, difficulty in counting, if we can't do that naturally, then we have to turn towards integration. Integration comes in whenever we have something which looks continuous but it is not, and when the items are really large in number, like that of infinity, if they are really infinite in number. So how I'm gonna transform this expression into integration now. Now let's see. Now we know that number of surfaces are going to be infinite and the surface actually is going to be really small. So I'm just going to put these two integral to denote that ultimately we are talking of the surface integral, surface area, because here the dot product is with respect to delta Si and S represent the surface. And now this integral itself means that no matter how much is the quantity, it's simply going to integrate the entire region. No matter how many surfaces you have considered, now we need not to count all those surfaces because that again would be really tedious job to do. What we can do is, when we have something like that, we can simply integrate it. We have to integrate it over small region, and we have to solve over small region, and then we will integrate it over the entire region. And for that we know the limits. And in case of surface, it's really easy. We need not to put even limits. So here I will only represent that it is the surface S, the original surface S that we started with. And here this del cross A would remain the same. And now since we have integration now, instead of this delta symbol, I'm going to use D and ds. No subscripts representing these I, because now this integral will do the job. We need not to count everything, because this, whenever we put subscripts, it's because we have to count each and every surface. But once you put integration, then integration will do the job. You need not to denote any number. You need not to tell how many number of surfaces you have drawn, because it has nothing to do with the number. It will only go for the continuity. It will start from one point and then it will just simply move along the whole surface by trapping all the region which is enclosed by the boundary. Thus, we can write down that line integral of vector function A over the closed curve C is equal to surface integral of the curl of vector function A over the normal component, or we can say surface integral of the normal component of the curl of vector function A over the surface S, which is being enclosed by the curve or boundary C. Here you can write it down like this also, A dot dr, and that is just to represent the normal component, dot n cap ds. This is our Stokes theorem. Now your task is to go through both the theorems that we have done, Gauss divergence and this Stokes theorem, and try to find out the points of distinction between the two I'm sure you will get a lot of points, because if you know it, go through the derivation once again. I have written the entire derivation in the way you have to write it in exam. You have to start with some general introduction, or you can just write a few lines for that, whatever you know about the figure. You can draw some general figure, and after that you have to write down the actual official statement, that I would say, because you cannot change anything from it. The definitions that we use in physics, the theorems, the statement of the theorem, you have to put them down, you have to pen them down exactly the way they are shown or written in books. And then you have to give the mathematical representation. After that, we'll start with the proof. We have used, first we started with one particular curve enclosing surfaces, then we divided it into two parts to get better understanding of how the things would come out. And then the final task was to show that actually we would divide the surface into large number of surfaces. Okay, and then this is the entire derivation. Whatever I have written, you have to write everything as it is in the exam. You cannot change the statement of the theorem, but you can definitely change the text, the proof portion. You can write down on your own. You can write in your own words. But the thing is, you have to represent everything what you are doing. Whatever you are doing, whatever step you are taking, you have to just write it down. Mark the equations properly so that we can use them, we can refer to them in our further derivation, and then just solve it. So this is the complete derivation, and if you just go through it, you would be able to actually write this down exactly in the exam. So this is what we have here now. This is the final answer. This is our Stokes theorem. Go through both the theorems. They are really important. One of the theorem definitely comes and it is asked in the exam. If it's a 5 marks question, the long answer question, definitely you would face either of the two theorems, and they are really important. And don't cram them. Try to understand them. I have done my level best in making you guys understand what these theorem actually mean. Why do we need them? And all these symbols. Now please remember, all these symbols that we are using, they have their meaning. Everything has some meaning, has some significance. So try to understand them, go through the videos once again, and if there is any problem, just mention in the comment box. I would definitely try to solve them. That's all for today. Thank you.